Hey, what's going on, folks? It's Mike here, and welcome to my next video in my modern C++ series. In today's video, we're going to be talking about another numeric algorithm known as reduce here. Now, reduce is going to be very similar to accumulate if you saw it in the last video. So let's go ahead and dive into CPP reference here and take a look at this numeric algorithm here. So I'm going to go ahead and scroll down here to this numeric operation here. And again, we looked at accumulate, which was a fold operation, or as we looked at it, some way to sum up values or multiply them or apply some other binary operation to successive elements. Now, reduce is very similar. In fact, you're going to see in the documentation, it says similar to accumulate except out of order. Okay, so what exactly does that mean? Let's click on reduce here, and let's go ahead and look at a little picture here. Recall last time where we looked at accumulate, and I basically stated that this was a way for us to transform many pieces of data, so a whole vector, for instance, to just one value here. And that's sort of a reduction algorithm. We've got the word reduction or reduce here, so I'm just going to put / reduce. Okay, these are our reduction algorithms, two of our reduction algorithms in the standard template library. And the basic idea is, or the main difference is we have the option to apply an execution policy. That is that we could actually do some of these operations in parallel here. For instance, if I'm going to add, I could add these operations successively or unsuccessively or out of order, whichever I prefer here, and potentially get some sort of performance boost to get one sort of value here. So I could do 1 plus 2 and get a 3, 3 plus 4, get a 7, get 11, a 15. And I could be doing this on separate threads, for example, if I had a large enough workload to make that worthwhile to do, and ultimately get the same value, 36 here. Now, of course, there are some restrictions. You have to make sure that there's no locking or dependencies or some of these different issues that come up. But again, that's the advantage of reduce here. Now, immediately you'll also notice with the page here on reduce that there are more overloads here. In fact, I'm seeing 6 here at this current time. And of course, we're going to pay attention to the since C++20 ones, which usually just the difference is they give us const expr support here. So we might be able to compute some things at compile time. But that's the basic idea here. Now, some of the overloads, including reduce here, don't even need an initial value. Now, as you remember, with accumulate, it was important for us to have that initial value because that's how we knew what type it was. And that's still sort of true with reduce. We still have to be a little bit careful here, meaning that if my input iterator, whatever the type is here, is a integer, it's just going to take whatever the initial value is for an integer when we construct it. So 0. Same thing if I'm doing some multiplication operation on a float. It's going to be, on 0.0, whatever the initial value is there. So again, that may or may not be the right thing that we want. So again, there are other overloads. This is probably the one that I'm using. Let's go to the const expr version, where I'm still specifying the initial value, and I'm still making sure that I specify the type with the precision I want. So maybe a double, a float, or an integer, depending on what my collection is that I'm iterating over. Okay, so that's what it looks like. And again, the main thing that's different here is the execution policy. Now, I've sort of skipped over this in a few of the previous videos, and I've mentioned that maybe we'll talk about the execution policies. We could talk about it here. I'll go ahead and just do an example or two. Let's see if we can generate something large enough to make it interesting here. But that's the basic idea here. Now, because we're doing operations that are out of order here, the behavior, as it says, is non-deterministic if the binary operation is not associative or commutative. So again, these go back to your basic mathematical properties that you learn in school. So commutative, meaning I can add numbers in different orders. And associative, meaning if I have 3 values, let me actually just illustrate it here. So if I have like A times, B times, C, that should be equivalent to doing the multiplication of A and B first times C here. Okay, so that's, again, the basic idea. And then commutative, again, the idea would be A plus B is equivalent to B plus A, or again, A times B is equivalent to B times A. Again, it just sort of depends. So you might want to think about that in certain cases here. Now, where we use the plus operation, so for instance, we can't really use this with, if we think about something common that we use the plus operator with, string concatenation. So just something to be careful with, or you have to think a little bit more about if you want to try to use reduce here. And I will say with reduce, it's also an interesting exercise to think about what types of operations you can actually implement in terms of reduce. That's probably a good exercise here, but let's go ahead and just look at reduce itself. As far as the complexity, this is like a O of n operation in terms of how many elements that we're looking at, and then how expensive our binary operation is. So if our binary operation is just constant time, then this is a linear time complexity algorithm. Okay, let's go ahead and take a look here at reduce here. Now I think in this example, what they've got here is they're basically checking, or we're checking our compiler to see if there's support here for the execution policy. So let's even see on my machine here. Let's go ahead and try this out and see if I have std execution and if that will compile here. Let's go ahead here. Again, I haven't done too much with it, but seems like we can at least include the header here. And let's try a little reduce operation here. So let's create a vector v here. I'm going to be explicit with the types here. Let's just use integers for now. 1, 2, 3, 4, 5, 6, 7, 8. That's what we did last time. And let's create another vector v2. Here we'll have v1 and v2. Let's do a let's do this on v1. Let's go ahead and call std reduce. And let's just go ahead and first make sure that it's working by doing on v1 begin, v2 end. And I'll show a couple of the different overloads here actually. Let's go ahead and do that. Just to make sure that we get the value that is correct. And oops, I've made a tiny mistake here. Is it 121? That's not right. Right, v1 end here. There we go. 36. Okay. So it's taking the initial value as 0. But again, I would recommend us to always provide in that additional value here is 0. Now, if you didn't watch my previous video on accumulate, I'll just remind you here that this is the value where the type is deduced from. So if I put 0 here, you know, that should basically match this type from the vector. If I have a bunch of floating point values here, and this is a vector of floats, for instance, and I put 0 here as an integer, I'm going to get an issue with the precision here, right? It's going to accumulate into a integer value. Okay, so you have to be a little bit careful about that. So I'm going to say generally, I recommend having the initial value and make sure it is the right type. Okay, so that's the basic idea. Now the other thing I'll go ahead and show you, let's go ahead and look at our other overloads here. We can pass in the execution type. We can find this from one of the examples. Let's go ahead and see here. Now they've pound defined some nicer ways to do this with sequential execution and parallel execution. So that's what they've done here in this particular example. But I'm actually just going to write it out. And again, these are the execution policies, which let's see here. If they define them, I guess they just have the policies here. Let's go ahead and click on these here. And I believe there are 4 execution. Yeah, these are the 4 execution policies here. So sequential, again, is basically not going to change anything with what we're executing, right? That's going to do like basically the same behavior as accumulate. Parallel is going to, and again, this is assuming that you know your operations are associative and commutative, try to give you some speed advantage by potentially using multiple threads or these types of things behind the scenes, okay? So that's the idea, and that's pretty much all there is to it. So let's try to use one here. Let's just grab it, hit std execution par. I'm gonna try here. And that's our first parameter here, std execution par. And let's see if we get the same value here. Now let's go ahead and just do par. And by default, we are doing sequential execution in our code. So again, getting the same result here. So no problem again, with this addition example. So you could try this. Effectively, this is a way for you to get, free performance bonus in your code without having to change anything, right? You just do a one-liner here. Don't have to mess with loops, initializing threads, anything like this. So these are big wins for the standard template library by having these sort of functionality built in. Other languages have similar things. D language has .parallel. I think other languages like Haskell have like algorithms prefixed with a P and these sorts of things. So again, this is really nice. This exists in the C++ standard library, and since C++ 17, you have reduce, and now you can take advantage of this. All right, folks, so with that said, I'm going to go ahead and end this video on reduce here, but I'll give you a little bit of a challenge here. You can think about, we looked at one of the overloads here. Actually, let's just go look at one other overload here before I end it. We have binary operations here. So you could think about, if you could have like a true or a false, or reduce some collection down to one number, or write some sort of, index of operation, or, element exists in some collection. I mean, these are the types of different things that you could implement in terms of reduce. Again, there might be faster ways to do it, but it is kind of neat just to think about this as a sort of fundamental operation. Reduce and accumulate, right? These sort of fold operations. Anyways, folks, with that said, I'll go ahead and end it there now. And of course, you can follow along on course.mshaw.io, track your progress through all these lessons here in the C++ programming series, as well as there's other series I've got here. My software design series may also be relevant for you if you're following along on this series. But anyways, folks, with that said, hope you enjoyed that lesson. Hope you're enjoying these videos. And yeah, let me know what you know about reduce, if you've used the parallel execution algorithms in any way that's been meaningful. I'd be really curious to hear about your benchmarks below in the discussion. Anyways, with that said, folks, thanks for your time and attention as always, and I'll look forward to seeing you in the next one.